Our final speaker today is Professor Jiang. The title is Integrability Breaking and Soliton Confinement. Please.
Okay, thank you very much. It's always nice to visit BIMSA. We have so many friends here. This talk will mainly be a physics talk, but I hope it can still be interesting for our mathematician friends. So by physics talk, usually it means you have more diagrams and less formulas, and then approximations are usually used. So the title today is Integrability Breaking and Soliton Confinement, because I believe most of the audience are not very familiar with these concepts. So I will spend quite some time actually explaining what is soliton confinement and why it's interesting. And then at the end, I will present our recent results. So this work is this talk is based on this work which we put out in February and in collaboration with Wu Jianda in Shanghai Jiaotong University and his student Gao Yunjing. So let me start with integrability, which is one of the things of this workshop. So we know that integrable models are fascinating many-body systems. So here I'm more taking the point of view of content integrability. So we know that such systems usually have a lot of conserved charges, conserved currents, and then conserved charges. And I think in the morning, Professor Qiao gave a very beautiful summary of classical integrability. And typically, because you have so many symmetries, if you go to the quantum regime, you think of the system as particles scattering with each other. And due to integrability, typically a very complicated m-particle scattering will be factorized into a sequence of two-particle scattering. And then all the dynamical information are contained in the two-particle scattering S matrix. And then this usually results in the exact solvability of such models. But today, I'm going to talk about breaking integrability. So why would I want to do that? First of all, of course, our universe is not integrable. Otherwise, we won't even be here. And also, as an academic question, actually, integrability breaking is a very deep and highly interesting question. Suppose I start with an integrable system. What will happen if I break it weakly? And then if the techniques we developed for integrable models can be of any use to some non-integrable systems. So these are the questions that we want to understand better. For example, in classical integrable models, we know that there's this famous KAM theorem, which tells you what happens if you break a classical integrable model in a weak sense. And this is a very deep and famous theorem in dynamical system. So if we turn to the quantum regime, many things that in integrable system cannot happen will start to happen. For example, in an integrable system, typically the particles are stable. But now, if you break integrability, particles will start to decay. And then in a scattering process, you'll be able to generate new asymptotic particles. And also, you have interesting phenomenon in quantum field theory, such as the forced vacuum decay. And also, the focus today will be the soliton confinement, which is something you will see when you break integrability. Since we're talking about confinement, let me say a few words. Confinement is actually one of the most fundamental open questions in theoretical physics. By this confinement, I mean the confinement in QCD. So essentially, what does confinement mean? It means that in a theory, that the fundamental particles of your theory cannot be detected. So what you can detect are their bound state. For example, in QCD, quantum chromodynamics, the fundamental particles we have are the quarks and the gluons. But we never see a single quark or single gluon in the experiment. Instead, what we can see are mesons, which are the bound state of two quarks, and baryons, which are the bound states of 3 quarks, and gluons, which are bound states of the gluons. So of course, QCD, the confinement in QCD is a very, very important question, and then we always want to have better understanding. But I want to emphasize that confinement as a phenomenon does not only exist in QCD. It also exists in other systems. For example, in many low-dimensional quantum many body systems, we will also see the phenomenon of confinement, and we will be discussing this phenomenon today. And of course, they are related. At the very end of my talk, I'm going to compare something between QCD, two-dimensional QCD, and this and the Ising system that I'm going to discuss. So now let's get into the subject, which is the confinement. First, I will introduce confinement in Ising field theory. So I will give you first the physical picture. As I promised, you will have more pictures. So we are familiar, or at least assume that we are familiar with Ising model. You can think either as a two-dimensional classical statistical model, or you can think of it as a quantum one-dimensional quantum chain. So it's well known that this model has a second-order phase transition at certain critical value, let's call Tc. And if our temperature is lower than this Tc, then this model has two degenerate vacuums. Suppose I don't put in any magnetic field yet. So you have one vacuum, which is all the spins pointing up, and then another vacuum, which is all the spins pointing down. So the two of them will have the same energy. So they are both vacuum. Now you start to ask that on top of this vacuum, what are the fundamental excitations? What are the excited states? Well, it turns out the fundamental excitations are the so-called kink and anti-kink. So why is that? Because the vacuum state, because all the spins are the same, are in the same direction, so you don't cost extra energy. So the rule of the game, which is set by the Ising Hamiltonian, is that if the two neighboring spins have different direction, you need to pay some extra energy. Okay? So you see, from this configuration, starting from the left, you have all spins up. Then at some point, you start to flip all spins down. So you realize only at this point, you need to pay some extra energy. So you can pay that because it's, well, minimum amount of energy. And then, so this configuration is what we call a kink. And here is what we call an anti-kink, which is you start with spins down, and then you go to spins out. Okay? So these are the fundamental excitations. And in the continuum limit, such kink and anti-kink, they really become a fermion in the field theory. So these are like two fundamental particles. Now, suppose now I start to impose some magnetic field, suppose in up direction. Then among these two vacuum, one of them will be the true vacuum, which is along the direction of the magnetic field, and the other will be the false vacuum. Because if you flip the spin, you need to do some work to resist this magnetic field. So then this configuration actually costs infinite amount of energy and is highly unstable. So it will start to decay. Now, you ask that, okay, now in the presence of magnetic field, what is my fundamental excitations? You can imagine, suppose I still want to excite a kink like before, then in this shaded part, I need to flip down infinite amount of spins. Suppose I'm considering an infinite long chain. So this means that the previous kink now will take you an infinite amount of energy to excite. So this is not a fundamental excitation you can have in your system. So a single kink or anti-kink cannot be excited. What can be excited is this guy. Suppose I take this configuration, so all the spins up, but apart from the finite number of spins, I put the spin down. So here we have this situation. Because I'm only flipping down some finite amount of spins, so I pay only finite amount of energy here, and then also here, and also here. And if you think in terms of kink and anti-kink, in the left, you go from spin up to spin down. So at this point, it's like you have a particle called kink. And then you go to here, then you from spin down goes to spin up. This is like an anti-kink. Now imagine these two guys as two particles. Then this spin configuration is like a bound state, you are bounding two particles. And what this guy in between is like a string connecting them. Why is like a string? Because you can imagine that if this number of spin down is larger and larger, then you need to cost more and more energy proportional to the magnetic field and proportional to the length of this down spins. Okay, so this is like if you stretch a spring, if you stretch a string, you will cost more and more energy. So this is like a linear potential which binding these two particles. So this is the basic picture of a soliton confinement in the Ising model. Now what I just described to you is actually one example of a more general phenomenon. So you can imagine more general situations. If you start with a theory with multiple degenerate vacua, not just two, say you have Q of them. And then suppose in this system, the fundamental excitations are the kinks which connecting different vacua. And then these kinks, typically in an integrable model, they can interact with each other in an integrable way, meaning that they are asymmetrics, factorized, satisfy Yang-Baxter equations, and so on. And then on top of that, if you start to turn on some non-local interaction, like the magnetic field I just put, this will typically break integrability and start to confine these solitons. So apart from Ising model, there are other examples. For example, you can have Q-state Potts model with a magnetic field. And you can have a double period Sine-Gordon model, or you can have some XXS spin chain with staggered magnetic field, or some spin ladder system. Okay? So I just explained in the lattice model what are soliton confinement and why they are confining. Now the question is, suppose now I go to the continuum limit, and we know that in the continuum limit, the Ising model is described by the Ising field theory. Now since you have these mesons in the lattice model, a natural question is, can we compute the meson spectrum in the corresponding Ising field theory? Namely, if you go to the Ising field theory, you must be able to see these spectrums. And the question is, can you actually calculate this meson spectrum? So this is a well-defined and interesting theoretical question. So I'm going to present to you several theoretical works which solve this problem partially. So some are more powerful than others. So since we are dealing with Ising field theory, let me use one slide to explain the Ising field theory. Just to make sure we are on the same page. As I said before, if we are at a critical point, a second order phase transition, then this system is critical. So at that point, it will be described by some conformal field theory. So this A CFT is the action of CFT. And this is a famous conformal field theory. It's one of the minimal models with central charge 1/2, and it has two relevant operators. One is called energy density. The other is called spin density. And they have physical meanings. So if you perturb your CFT with, say, energy density, physically what does it mean? It means that you change your temperature. You change your temperature from the critical temperature to some other temperature. So this will create some temperature difference. And this has a dimension of a mass. And what about if you turn on this spin density, like here? Well, this physically means you start to impose some magnetic field. Okay? So basically, these two operators just does two very simple things. One is changing the temperature. The other is putting the magnetic field. And interesting point is that if you only turn on one of them, say if you only turn on epsilon or if you only turn on sigma, they are integrable. So if you turn on just the epsilon, you will get a free massive Majorana fermion, which is free and is integrable. If you only turn on this sigma, you will get this famous Zamolodchikov's E8 theory, which is a non-trivial integrable quantum field theory, but anyway, it's integrable. And the funny thing is, if you turn on both of them, it's non-integrable. So it's a generic two-dimensional quantum field theory. And for this reason, the Ising field theory is a really good prototype to study any two-dimensional quantum field theory because you have CFT, you have integrable QFT, and you have non-integrable QFT. And this describes a lot of interesting phenomena. And yeah, this is what I just said. Now, let's come back to the question of a meson spectrum in Ising field theory. So first, it happens in this regime where the theory is not integrable. Okay, so you need both the temperature is off-critical and also you have magnetic field. So the question of determining this meson spectrum actually dates back to this work by McCoy and Wu in 1978. So what is their strategy? So back then in the 1970s, McCoy and Wu and other collaborators, they did a lot of work in computing correlation functions of the Ising lattice model. So they have a lot of experience on that. And their approach, basically the strategy is the following. So you compute, or they compute, the two-point function of the Ising lattice model. So two-dimensional Ising, one spin at the origin and the other spin at somewhere else. In the presence of a magnetic field, you want to compute this thing analytically. So then in the continuum limit, this two-point function will become a two-point function in the field theory. And if you can compute this thing non-perturbatively, then by looking at the analytic property of this two-point function, you can deduce what is the particle spectrum in your theory. So basically, this is the strategy they take. So in a bit more detail, they are able to show that in the limit where these two spins are very far away from each other, they can have this asymptotic behavior. Okay, so this is what they extract from the exact computations on the lattice model, and taking the continuum limit carefully, they found this two-point function in the field theory has this behavior. And what is particularly interesting is this in the exponent. In the exponent, you have 2 plus this kappa LH. So this H is the magnetic field. And this 2 plus kappa LH is related to the meson spectrum. So this kappa H and then this AH, they can all be expanded as a series in H. And using this approach, McCoy and Wu was able to determine the leading order in H. Okay, so they determined this kappa LH, the leading order in H, and then also this. And one interesting thing is here the leading order starts with a power of 2/3. And what are these? The lambda L. So there's still some funny number called lambda L. So the lambda L turns out to be the solution of this equation. And this equation is written in terms of Bessel functions. So we can remember these two Bessel functions with this index 1/3 and minus 1/3 because later it will appear again. So if you look at this function, it will in the positive real axis, you will see this vibration, and it will have infinitely many discrete zeros. So the statement is that for each zero of this guy, you will have one lambda, and for each lambda, you will have each kappa lambda. So then what does this kappa lambda mean? And we can look at this the analytic behavior of this two-point function in the Fourier space, and you can realize by some standard field theory analysis, this kappa L is related to the pole of the two-point function in the momentum space. So you will see many infinitely many poles that is located on the imaginary axis at the position 2 plus kappa L. And this is interpreted as infinitely many mesons with mass 2 plus kappa L times m, where this small m is the mass of a single quark or single fermion. So you can see that 2m correspond to the mass of the two fermions, and then this kappa L correspond to the binding energy between these quarks. So the remark is that if you look at this two-point function at h equals to 0, you will see actually from 2i, you will have a branch cut. But if you turn on this H, you'll find immediately this branch cut will break into infinitely many poles. So this corresponds to the physical phenomenon. If you have zero magnetic field, you don't have this confined mesons. But if you have a magnetic field, the solitons will start to confine. So that is why their paper has this name, breaking up of the cut in two-point function. This is what it means. So this is the first hint or the first analytical derivation that in the Ising field theory, you actually have infinitely many mesons with this mass. Okay, and this, of course, is they derive it by some very complicated analytical derivation and resummation. Now let's take a physicist point of view. Take a physicist approach. We want to use a very cheap way to rederive the same result. So what is a cheap way? We use our physical intuition. Let's imagine you have two particles, this red and the green dot, and then we just bind them by putting in hand some linear potential. So, and this linear potential is proportional to the distance between these two particles, and then the sigma bar and H plays the role of something like a string tension. So the energy of each particle will be given by this omega p, where p is the momentum of the particle. And in the relativistic system, you have this dispersion relation, and this is the Hamiltonian, okay? So we will even simplify this problem a bit further. We take the non-relativistic limit, and then this omega can be approximated by this quantity. And then we go to the center of mass frame. We take P1 equals to P, and the P2 equals to minus P, and then we define X equals to X1 minus X2. After doing this, the Hamiltonian is approximated by this guy. And now we do the quantization. Basically, we just replace this P by some partial X. So then to determine the spectrum of this system, all you need to do is to solve this Schrödinger equation. And interestingly, this is exactly solvable Schrödinger equation. So its eigenfunction is just the Airy function. Yes. Yes, exactly. So it's you can solve it by the Airy function, and then how can we determine this delta En? Well, from quantum mechanics, you need some boundary condition. So the boundary condition we impose here is that because we are dealing with fermions, suppose we are dealing with fermions, then at x equal to 0, the wave function is 0. And by this condition, you can find this delta En. Or you can, this is like a quantization condition, and you can find the meson spectrum like this. So of course, since we're dealing with the Airy function, and so this energy will be related to the zeros of Airy function. So what I call Zn, okay? And so this is a spectrum we found by this very cheap approach. And now you realize that Airy function is related to the Bessel function, exactly at this index. We have seen this equation before, okay? So previously in the McCoy and the Wu approach, we write the zeros of this right-hand side, and now we are just writing it in the Airy function. And you see, we obtain, if you do it carefully, you can find that you obtain exactly the same result of McCoy and Wu. And this is like a 3-line derivation, which is a cheap method. But of course, why this method works, it is telling you that this is capturing the main physics of the problem. Indeed, these mesons, or what observed by McCoy and Wu, is really just the confinement of solitons. That's why it works. But let's say both of these methods, they work at the leading order of H, okay? Of course, the complete spectrum, if you want to do better, so we ask the question, can we find a meson spectrum at any order in H? Can we do better than McCoy and Wu, and also this linear potential approximation? So the question is, the answer is yes. And then we need a more powerful method, which is called the beta-salpeter equation. So this is a standard approach in, say, nuclear physics and high energy physics to find a spectrum of of a bounded two-body problem. It was invented by Hans Bethe and also Erwin Salpeter in the 50s, first in the nuclear physics, but then it was adapted to this question in the Ising field theory by Fonseca and Zamolodchikov, who have a series of works trying to determine the particle spectrum in Ising field theory. So basically, the Bethe-Salpeter equation is an integral equation which describes two-particle bound states. And to do that, we first write our Hamiltonian, the Ising field theory Hamiltonian, like this, where we have a H0 part, and then we have another part, which is the perturbation by the sigma field. Recall that the sigma is the spin density. So here is we're imposing some magnetic field. And this is the free part. So because the H0 is just a free Majorana fermion, so you can easily quantize it, and then you can write the Hamiltonian in this free form, which is a quadratic form in terms of the CP and the CP dagger, which are the creation and annihilation operators in the free fermion theory. And you can look, so the Hilbert space also has a very simple structure. They are just spanned by this m-particle states. And this m-particle states is obtained by creating fermions from the vacuum. So an important input of the Bethe-Salpeter equation is the following matrix element. So the spin field is the field that we use to perturb the free theory. And then we need to know this matrix element because you will see that it will appear later. And the good news is that this is known. This is known exactly. So then what we do? We do the following approximation. Suppose we want to find the eigenstate of the full Hamiltonian H. Then we can expand this eigenstate in terms of two-particle states, four-particle states. We only consider the even number of particle states because of this Z2 symmetry. And so a generic two-particle state will take this form. So you span it by a two-particle basis, and then this psi is the wave function, is a generic wave function. So now, suppose I want to find an eigenstate and the eigenvalue, I can write down this equation, and then I want to project this equation onto some basis state, P1, P2. So, and you can imagine what can happen. On the right-hand side, if you do this projection, you basically just project out this wave function, okay? So that's here. And I just write this E as epsilon P1 plus epsilon P2 minus delta E. So this is the right-hand side. And on the left-hand side, you will sandwich this H. And remember, in this H, there's a spin density field. So then you will have some matrix element of this field, and this will result in this right-hand side. So yeah, so basically the first step is that, in principle, if you want to solve the problem rigorously, you should take into account of all particle states. But here, using the Bethe-Salpeter equation, we're just making a two-particle truncation. So we truncate this series to the two-particle sector. And then we first obtain this equation. This is an integral equation. So let me explain a little bit more. These epsilons are the energy of a single particle. And this delta E is actually the thing that we want to find. This is the energy difference beyond the ground state. And this F0 is the string tension. And this G on the right-hand side, which is the integral kernel, is related to the matrix element of the spin density field. And we know that. So then the next step is we need to do some simplification. Using the fact that momentum is conserved, so we can denote the sum of two P1 and P2, and the Q1 and Q2 to be P, and then we take their difference to be small p and the small q, and rewrite this wave function by extracting out some delta function. You will simplify a little bit the equation on previous slide. So this is the simplified equation you have here. And as a last step, which is something more physical, so maybe I will just very briefly comment, but skip this part. So you need to take the limit where p goes to infinity. So this limit, this is called an infinite momentum frame, and we need to do this step because we start with a relativistic two-dimensional quantum field theory, and if you truncate at a two-particle sector, this will typically break Lorentz invariance. And then taking this infinite momentum limit, it has the effect of restoring the Lorentz invariance in the two-particle sector. And then you need to do this limit very carefully, and suppose you can do it very carefully, you will obtain this final equation. So this is the final beta salpeter equation that we are really going to solve. And then this, you can do a change of, so this is the explicit form. So you see this is indeed an integral equation, and this FUV is the kernel, and it comes from the matrix element, which we know of the spin field. So we need to solve this equation to find this phi and this m square simultaneously, because this m square is essentially the meson spectrum that we are interested in. So, and then you can do some change of variables to make it look a bit simpler, like this. So the upshot is that this equation actually, it turns out, is simple enough that you can solve it analytically perturbatively. So either you can solve it perturbatively or you can solve it numerically. So it's not very hard to solve this equation numerically, and then we can find this mass spectrum. So let me just show you, if you try to solve this equation analytically, what will you find? So you need to do an expansion in this parameter t. So t is chi 1/3, and the chi is related to this h, which is the magnetic field. And then you can solve it order by order. You find that the first order, 1 plus z and t squared, this is the McCoy and Wu result. This is also our linear potential result. And then you can go on. With the beta salpeter equation, you can go on and find more and more terms. In principle, you can solve it at infinite order in this parameter t. Okay? So this is essentially the story. So there are two physical comments. One is that a legitimate question you might ask is that now in the beta salpeter equation, you are just doing two-particle truncation or approximation. So what happens? What are the effects of higher particle contributions? This is a legitimate question. And they will contribute in two ways. So some of this higher particle process will renormalize the mass and the string tension. So namely, it will change this small m square and this f0. And some other corrections will change the higher orders in the perturbative expansion. So it will change, for example, the result starting from t to the power of 8. And also, another question is, how do you make sure that your result is good? What can you compare to? And in quantum field theory, in 1 plus 1 dimensional quantum field theory, there are some approach which can give you the spectrum numerically, and this is called a truncated free fermionic space approach, or truncated conformal space approach. So there are this approach which you can use to find a spectrum numerically and compare with your solution of beta salpeter equation to make sure that you are doing the things in the correct way. Okay, so now comes to our recent work, which is the meson confinement in an Ising ladder. So what is a ladder? Previously, we have one Ising model, which is either the first line or the second line. Now imagine you have two Ising models, okay? So Ising model 1 and Ising model 2 with labels 1 and 2. And then you couple them. You couple them side by side via this sigma z field. So, and this part is the coupling of the two chains. Now, this system, you can also describe it in the scaling limit by some quantum field theory. And it takes this form, roughly. So this H1 and H2 are the Ising field theories of the first chain and the second chain. And then you have the interaction, which is described by coupling these spin density fields. So note here that both in chain 1 and chain 2, we didn't put in any magnetic field. So this is at zero magnetic field, but it still have confinement. And this confinement is due to the interaction between the chains. Okay? So the picture is the following. Again, we are in the low temperature regime, so you have two vacuum. One is all spins up, the other is all spins down. Now in this situation, you also cannot excite a kink and anti-kink. Why? Because if the spins of the two chains, say the upper chain and the lower chain, if at the same site, the spins have different direction, you need to pay some energy. And this is due to the interaction between the spins. So if you try to excite this configuration, then in the shaded part, again, you need to pay an infinite amount of energy, and likewise here. So then, what can you have? Well, you can have bound states. And since now we have two chains, you can imagine we can either confine the two particles on the same chain, or we can confine the particles from different chains. So we have more choices. And so the first choice is like this. So this is like from a kink to an anti-kink. So you only pay some energy here because, okay, energy here because it has different directions. Also here and also between the chains. So this is a finite amount of energy that you can pay. And then similar on the right picture. And in this chain system, in this ladder system, you also can have mesons that comes from confining fermions from different chains. And this is what we call the interchain mesons. And then you can have this interchain situation or this interchain mesons. So to sum up, basically, in the ladder system, you can have richer structure of mesons. Okay? And also ladder system is something very natural in experiments. You can see them in some quantum material, and you can engineer them in cold atom experiments. And that's why it's interesting. Okay, so suppose now we want to find this the spectrum of the ladder system. We can also first try our, say, cheap approach using linear potential approximation. And then you can write down this Schrodinger equation for the interchain meson. You find exactly the same Schrodinger equation. The only difference from the Ising case is that now the string tension is proportional to lambda, which is the coupling constant between the two chains, instead of h. So previously we have h, now the h is replaced by the interaction between the two chains. And then you impose the same boundary condition, and you find, of course, the same meson spectrum. Is the only thing different is the string tension is now changed. Okay? And for the interchain mesons, we can write down the same Schrodinger equation, but because now we have two chains, so there's a symmetry which is exchanging two chains. This is like a Z2 symmetry. And with respect to that symmetry, because the Hamiltonian is obviously symmetric, so this pi 1, 2 is exchanging these two chains. So you need to do some symmetrization and the anti-symmetrization of your wave function. Okay, so it just separates into two sectors. So one is this even sector, I denote by psi tilde plus, and the other is the odd sector, I denote by psi tilde minus. So the two sectors, they satisfy the same equation, but they have different boundary condition. The odd sector, because this is an odd function, so you have the same boundary condition as the Ising case, which is at 0, the wave function is 0. So you get the same mass spectrum. So this means that there's one branch of the interchain meson which is degenerate as the intrachain meson. Okay? And you will see that this degeneracy actually persists in the beta salpeter approach. Now, what's interesting is this new approach, this new branch, which is this even sector. So for this even sector, now the boundary condition is changed to this guy, you need to take a derivative with respect to the wave function. And then you can find the meson spectrum, which is different. And then this Zn tilde is related to the first derivative, to the zero of the first derivative of the Airy function. Okay, so this is what our simple analysis tells us. You have several branches, and two of them are degenerate, and then you have a new branch which involves some new numbers, Zn tilde. And now we can do the same thing in the beta-salpeter equation. Now we can use the beta-salpeter equation approach. Note that because we have two chains, so when we truncate to the two-particle sector, we have more choices. You can either put the two particles on the same chain or one particle at each chain. So this is the first two lines correspond to the case where, say, you put both particles on chain 1 or you put both particles on chain 2. So you need two different wave functions to describe them. And the last line is that you put one particle on each chain, so you need yet another wave function. So in this system, you have several wave functions that you need to take into account. But anyway, we can do that. We can start with the Schrödinger equation, and then we can project out. Say, now we need to project out in three cases. We can project out on this basis state, and then you see that you will have some mixing between these wave functions, psi 2, 0 and the psi 0, 2. So you have some mixing between these wave functions. And you can easily imagine that you will have a system of equations instead of one equation, right? You have a system of equations involving these three wave functions. And you will have several new kernels, but because each kernel only involves this type of form factors, then they are known explicitly. So anyway, after you obtain this system, because it's actually a linear system, so you can decouple them easily. So finally, you can decouple them into three sets of beta-salpeter of Ising-like equations. So then the rest is similar. You go to the center of mass frame, you take the p goes to infinity limit, and so this is the three decoupled beta-salpeter equation you obtain. So they look very similar to what we have seen in the Ising case. And in the last term, we also need to do some symmetrization and anti-symmetrization due to the Z2 symmetry of swapping the two chains. So after that, we obtain actually four sectors. So each theta, so theta plus 2, theta minus 2, theta plus 1, theta minus 1. So we have four sectors of different mesons. So each sector, you have a set of mesons, and they can be obtained by solving this beta-salpeter equation. And as I said before, you realize that just by looking at the beta-salpeter equation, this sigma 2 minus and this sigma 1 minus, they are exactly degenerate. So this degeneracy persists. And then, okay, you can follow the same way to solve these equations perturbatively. And so this is a new case where you have Zn tilde, and then you can solve it order by order if you want. And yes, what about? Yeah, you can also solve it numerically. So this is a numerical solution. This is rather smooth. And I just show the first few mesons in this plot. And so after comparing this result with this with a numerical result from truncated fermionic space approach, you realize that actually in a rather wide range of this parameter space, it works well, but it doesn't work that well near the origin. And in the origin, we need to renormalize the string tension and the mass spectrum and the fermionic mass, which comes from some corrections of higher particle contributions. And after you do that renormalization, actually the beta-salpeter equation, although it's like a two-particle truncation, it works actually quite well compared with the numerical solution. Okay. So finally, before I end, just as I promised, I want to show you something that between QCD and our chain system. So this is, in this part, this is the beta-salpeter equation of the 2D QCD, which is derived by Toft himself in the 1970s. And this alpha A and the alpha B are related to the quark mass in the QCD. So this lambda n is related to the meson in the QCD, to the meson mass in the QCD. And you see that, and this is our beta-salpeter equation. So here I generalize slightly. So we can have a chain system where the mass in the two chains are different. So then you have this generalized beta-salpeter equation for the interchain meson. And you find the left-hand side is almost identical, right? So you just replace this lambda by some m squared and replace this alpha by some m. And the right-hand side is also quite similar. So there's a leading divergence, which is theta equals theta prime, all controlled by this sinh square. So here you just have a simple sinh square. Here you have something more, okay? But this sinh square actually corresponds to this linear potential, if you analyze it. So it means that at the leading order, the physics of this QCD is exactly the same as the physics of this ladder system. So actually, by studying this ladder system, we can learn something about, well, lower dimensional QCD. So although they come from very different origins, one from high energy physics, the other from more like statistical mechanics or condensed matter system, we share the same physics. Okay. So now let me conclude. So I hope I convince you that soliton confinement is some intriguing phenomenon when you break integrability. And then there are several methods to compute the meson spectrum in Ising field theory, such as the beta-salpeter equation, McCoy and Wu approach, and so on. And we analyze a new system, which is an Ising ladder system, and we found new type of mesons, which are the interchain mesons. And well, in the future, there are a lot to do. So first, these mesons, as we are physicists, then we can ask, can we detect these mesons in real-life experiments? What are their influence for the dynamical behavior of your system? So this is one thing. And then we can also try to determine what is the full particle spectrum. By this I mean, the mesons we see is at the low temperature limit. So what happens at the high temperature limit? Can we determine everything, like in the Ising field theory? And then we can also imagine some more funny situations. Now we couple two chains. What about if we couple three chains? Can we have baryons? Can we have more exotic objects? Can we find their spectrum? And also, I made some comparison with, if you make some comparison with QCD, you'll realize the idea is very similar. So the McCoy and the Wu approach is very similar to lattice QCD. You break the system into a lattice model, and then you solve the lattice model. And this linear potential approach is very similar to some Fino approach to determine the QCD spectrum. And then there's something which QCD people derive, but is still lacking in our context, is something called QCD sum rule. And then I want to see if we can learn something from QCD, or we can borrow something here to understand QCD. So, and with that, thank you very much.
Thank you.
Nice talk, thank you. You see, I want this question. So now, can you organize your system of equation close to the zamological point? When do you sit down criticality in usual Ising, then you have a zamological base matrix, yes? System of equation should give the A zamological meson, right?
You mean this EA theory?
Yes.
Yes.
Can you organize such a thing? Then you have,
sure.
have exact solution.
We can see that. You can see that when you approach that point, exactly you see this, there will be eight stable particles.
Wow.
And 5 of them is above the threshold.
Yes.
So if you slightly away from this point, these guys will start to decay. But at that point, they are stable because of integrability. And then 3 of them is below the threshold, so they're naturally stable. Yeah, you can see that, exactly.
Very good, because some of those mesons experimentally.
Yes. Yes, and one of the reasons we start doing this business is that we actually, first, if you consider this chain, this ladder system, there's also this similar point, which is the D8 theory. And we want to understand what happens if we go away from the D8 point.
Yes.
That's why we start to do this beta salpeter analysis. Yeah.
Thank you.
Thank you. Any other question?
I have. Yeah, so very good talk, but just one precision. When the first is, when you talk about the first beta salpeter, before adding, sorry, before adding, I apologize, before adding the laddering. So when you would add up to the beta salpeter, this high particle, so am I correct that this would end up, even before ladders, this would end up in the renormalizability of the quark mass and the coupling?
Can you say it again?
When you start adding not just the beta salpeter truncation at the 2 particle, but the higher particle corrections, bound states, does that lead only to renormalization of the quark mass and the coupling?
Not only that.
Right.
So part of it renormalize this physical parameters. The other also change the result at higher orders.
Yeah, that's my point. So qualitatively, does it shift the roots of the area equation, or there is something else?
Oh no! Once you go beyond this leading order, this area potential, this linear potential approximation is not there. It only captures the physics at the leading order.
No, beyond. That's what I'm saying. Not the linear approximation, but the beta salpeter is this.
Yeah, beta salpeter captures more. Yes. Yeah, definitely.
Do you see any other new effects when you do this higher particle, or you don't know?
Not that much, because as you see, if you solve it,
numerically, I see that it is important at the very beginning, right?
Yes, if you solve it, then because at the beginning this approximation is not very good, but then you can see in the majority of the parameter space, it actually fits well with this TFSSA approach, right, which says that although I'm only doing 2 particle approximation, but it's surprisingly good compared to the exact result.
I see. Yeah.
But one thing that beta salpeter equation cannot see is that at some point these particles will start to decay. But if you just solve beta salpeter equation, you don't see this decay. Sure. So you only see that decay using this
integrability equation. Of course, it will not give you. Yeah. But also another point. Have you thought? I think it might be particularly interesting. Like you said, part of my point was if you start adding ladders, but adding in such ways that the interaction potential is somewhat equidistant or similar, right, and then taking continuum limit of this.
Now that's horrible, no? That looks insanely complicated. Yeah, but one question
actually,
is, yes.
Might be even better than finite number of them.
Okay, we'll see. But yeah, one question is, can you have more, apart from mesons, can you have more exotic bound states, like baryons, like even some 4 quark states? And you need richer structure to have these strange objects. Yeah.
Okay.
Can you develop this approach for boundary problems, so you have boundary bound states appearing?
We thought about it, but we haven't actually worked it out very carefully. Yeah, but that's a good question. Yes.
Okay.
Yeah. Because so far this question actually works on an infinite system. So what happens if you start to put on boundaries? That's interesting. Yeah, or semi-infinite. Yes. Then you have some situation bound state at the boundary and so on. Yes. Exactly.
Yeah. So I have a question about basically about the interchain meson that you mentioned.
Yes.
I thought that at least you need 4 particles. But I mean, if you just have 2, then you have to change the boundary conditions or something?
Let's see. Not really. So the physical picture is here.
Yeah, so you're changing somehow the boundary condition.
Oh.
Right. Okay.
Yeah. So what do you mean by boundary condition? Because here I'm going from up to down, so this is like
So you basically have just two kinks instead of a kink anti-kink bound state.
yeah, this is a two kink, and then yeah, this is also a two kink.
Yeah. Okay. So I thought that you need somehow a kink anti-kink to call a meson, but maybe I misunderstood this.
But this is that's the new beast. So in the same chain, yes, you need a kink and anti-kink.
Yeah.
But then since we're dealing with, since this is a new object, you see, you need to look at it, see if you pay only finite amount of energy. So you pay some energy here, and you pay some energy here, and that's it. So it's finite amount of energy, and here you pay a little bit more because you stretch these two particles away from each other, and so yeah, so this is some bound. Actually, this guy has a lower energy than the interchain meson. Yeah.
You see, I forgot. In the point of view, the Schrödinger equation electrical field. So this the zeros of area function now. What is this? It should be unphysical points, yes?
What?
What is this? Bound states. Right hand side we have the sum of the Bessel function.
Yeah.
In a zeros area function, what means for the Schrödinger equation for electrical field?
I don't understand
So
the question.
you see that you write the Schrödinger equation for the area function, right?
Right.
Functions.
Right.
But exists these zeros.
Yes.
You know from the Bessel function. What
Yes.
means for this physical problem?
Oh, these are actually the mesons. So you can have infinitely many mesons, but not all of them are stable. So if you have mesons whose mass is larger than twice the lightest meson, this is called above the threshold. So these guys are unstable, and only the guys below this threshold is stable. But in principle, if you just look at the equation, you would say that these are all the mesons, because you see you have two particles. You can stretch them. You can stretch them. You can stretch them a long way, right? So this corresponds to all different these infinitely many zeros of the area function, because you can have a longer and longer string between the two particles. But of course, if you pull it too much, these strings will start to break up and then decay into some smaller strings. And then this is the saying that these heavier mesons are not really stable. But in principle, theoretically, they could be there.
Okay, thank you. It's pity to interrupt this active discussion, but well, let's continue during the lunch. And
Okay.
so thank the speaker again.